I want you to be mesmerized and study the screen.
It's the tangent line.
So I need you to be hypnotized by the graph, the animation here. And then you have to explain what's going on. What are the relationships that you see within the graph?
It's the tangent line. Across the parabola.
So this is actually the function, the blue one that you see here. This is the one that we put up yesterday. I'll show you how we come about it. But in an 8-second flight path, we reach a maximum right here. And I'm going to recap what I said yesterday because it is what we're going to study for the next 3 months. Okay? So it's kind of a good idea to get down what is the point of the next 3 months, and that is to understand this thing called the derivative. There's so many things that are related to it. So the first thing I want you to know is, do you see how this tangent line, how it smoothly goes across? Okay? The tangent line only touches the graph at one place at any given time. It's only a single point. Okay? And the thing that I was talking about yesterday, in a nutshell, Descartes said there had to be something that's connecting the position function. This is the blue one. It's called the position function because it tells the position of the ball in space, okay, in the air, above ground, at any given time. So this blue graph is a function that if we plug in the time, any time, and we travel it up, it tells you exactly how high the ball was. Okay? And there's no calculus there. That's just pre-calculus stuff. It's the height of the ball. But here's what he said. He said, you know, that tangent line has something to do with how fast the ball is traveling. And he noticed it because he said, if I stop this thing right at time equals 4, it's the moment that the ball reaches the peak. And the ball goes up. And it seems to like freeze for just a moment, doesn't it? It's going up, and then it freezes, and then it comes down. Because when it's at the top, it's not going up, right? But it's not going down. Okay? So it's at that time. So the slope here is 0. And Descartes said, hey, what if that's connected to the speed at which the ball is moving? He was the first guy to do it. And it was the breakthrough of just epic proportion that changed the course of the world. The slope here. And it turns out that, okay, that sounds good, but what if we test the other ones? And he said, well, you know, the slope way over here on the left side, that slope is really steep. And I know that when I launch the ball out of the spudinator, it's going the fastest when it first comes out. And then gravity has this effect where it's slowing it down as it goes up. And he said, look at that slope. The slope here is some positive number, some big positive number. And as we move to the right, that slope gets smaller. So as I go through here, look at that slope. See, it's getting smaller and smaller and smaller and smaller and smaller. It's still all positive until we hit exactly 4. Okay? At that moment, it's at 0. Then he said, now take a look at this. If it goes past this, all of these slopes are negative until we reach it, till it hits the ground. And he proposed this. He said that the slope of the line tangent to the position function, that slope, that number, whatever you get for that number, is the velocity of the object. Whatever that answer is, whatever that slope is, he says that's how fast it's going. And not only how fast, which direction? Positive going up, negative going down. Okay? Descartes did this, but he couldn't figure out how to actually find the actual number, to find the slope. Because the problem is, to find the slope at any given point, you only have a single point. And it was impossible to find the slope of a line that passes through one point, because there's an infinite number of possibilities. And then he died, remember? And so he left this earth not knowing what he always wanted to know. And then Newton came along and Leibniz came along, and they took what he learned here and they developed calculus. They developed the limit process and calculus to find it. I want to show you one thing. Newton and Leibniz said, you know, Descartes was right on the money. And here's why. Here's the justification for why he was right on the money. Descartes said that the slope of the line tangent to the position function was the velocity of the object at that precise moment. And they proved it by saying this. Well, wait a second. What are the units on the slope? Rise over run, right? So if I'm going to start here and I go up this far, okay, and then I go over this far, I can find the slope of that line. And look at what we're using. We're using feet, so we're rising feet, and we're running seconds. So what are the units on the slope? Feet per second. Bam. Velocity. See the connection? So we don't call it slope, we call it rate of change, but the slope is a rate of change. It tells you how fast you're going. Okay? This was the fundamental thing that changed the world, and it's all a matter of just taking a look at the units on the item. Okay? All right. So we're going to do a quick development of where this formula came from based on the 8 seconds. And then we're going to start our next unit. This was just taking a couple of days to introduce you to what it is that this is all involved. And I made this too, just for you guys, to make it look for that. I think it looks pretty good. Yeah, boy, what's that green line? Don't ask me. Well, you can ask me, but I won't answer. The green line. Everybody look at it. What does the green line have to do with this graph? Nope. It's not when you add up to 2. Who said it? Velocity. He's correct. Look at the green line. Time equals 0. What's on the green line? It's up here. time equals 0, this green line is the slope at time equals 0, right there. That's the slope. At time equals 4, what's the slope? 0. The green line tracks the slope. And believe it or not, the slope actually is a line. It's a linear function of what the slope is at any given time. And look at this. At time equals 8, the slope is negative. It's exactly the opposite of this one. Because when an object takes off, its speed is exactly the same, not velocity, its speed is exactly the same as when it hits the ground. Why is it negative? You throw an object up. Through this whole time, we talk about velocity. Okay, let's do a quick thing on velocity. Velocity is speed with direction. Speed just tells you how fast you're going. Velocity is the speed, but then plus or minus. If an object is going up, it has positive velocity. And then when it's going down, it has negative velocity. So when it hits the ground, in this one I think the slope is 128 feet per second. So at the very, very beginning, this thing shot out of the cannon at 128 feet per second. When it landed, the velocity was negative 128 feet per second. Make sense? Okay, these are fundamental concepts. They're physics concepts that are so important in understanding calculus. Okay. Now, I got to be honest with you. It's been kind of easy the first couple of weeks here, hasn't it been? No, be honest. Had to do a couple of homework assignments. You come here, listen to the show, do the things, okay? But this has all been just laying a foundation, because starting any time right around now the work's going to come, okay? So I want to prepare you that the work is going to come, and there's going to be a lot. You're going to have homework, you're going to have problem sets, you're going to have chapter summaries, you're going to have to be keeping up on everything. And I try to work with you, but just warning you that we're just on the cusp of starting to work. Okay? We've been kind of just building a little foundation before we start. Okay. And I can prove to you on the green line. I think I can click on the green line and get you that point. So if I click here, there it is. See, 0, 128? That's how fast it was going. Here, 4, 0. And over here, over here, 8, negative 28. See that? Okay, those are all the points. And that's the actual velocity. It's kind of cool that the velocity just forms this line, isn't it? You'd think it'd be more wiggly or something.
What's the point of the hx is equal to gc?
Okay, I don't have that one showing. So this is an extra feature that I put in here. Okay, can anybody tell me what this feature is? Tells you what the velocity is any given time. So the velocity, stop it at the bottom. There, that's negative 128. Then the velocity is 0 at the top. And then it's 128 here. It's actually just plotting what's the green line. I thought it'd be something interesting to look at. Okay. Well, the remainder of the class time is we're going to develop the formula that gets you the parabola for the position function that we figured out in class, or we launched, and then I'm going to show you how to get the velocity function using the definition of the derivative that we did to show you how they came up with the green numbers. Ready? Okay, they're all charged up tight today, I can see. Ready? Let's go! All right, round 2. Let's go! We have to figure out something on these. Yeah. Okay, so let's develop the position function. Here's what we established. The ball was in the air for 8 seconds. Okay? That's the only thing that we know. Okay? But if we do a little research, we can say that the general formula, the general position function, looks like this. Okay? And this one you should have down. We'll work with this several times. S of t, S for position. It's S actually for S for position in space. That's what it is. It's three-dimensional. Is equal to 1/2 gt squared plus v sub 0 t plus h sub 0. Okay? That's the general one. There's another one. This is for when you shoot an object straight up and it comes straight down. Okay? That's that one. If you shoot something at an angle, okay, then the position function changes. It's 1/2 gt squared plus the sine of the angle times the velocity times t plus h sub 0. So remember when we had it at an angle, we were shooting it at the tower? Okay, the sine of the angle, we put that in here. This will tell you the position at any given time. Yeah.
I started to work on the position function. I don't know if I wrote it wrong, but I had S of t 1/2 gt squared plus h.
And that's the one I'm going to write right now. Okay? And the third one is if you're standing on a building and you launch something off and you just drop it, okay? You just simply drop it, you let go. There's no initial velocity, you just let it go. No, I won't do it. You know what I was going to do, right? Just let it go. I'll burst into song at times in this class, just to warn you. And the last one here is 1/2 gt squared plus h sub 0. Okay? Okay, do you need to know what any of those letters mean? Okay, jot them down. G is the acceleration due to gravity. Okay? Newton came up with this in his universal law of gravity, and it means that the gravitational force on the moon or Pluto is different from that on Earth. Okay? But the formula is still the same. That's what's really cool about it. You just replace the gravity. T is in seconds. V sub 0. Physics people? Initial velocity. H sub 0? Initial height. Okay? All right, those are the three scenarios. Now, watch this. So this is in the development phase here. Remember yesterday we said, here's our thing, and it went for 8 seconds, and this 4 was at the top. Okay? The problem is, we cannot figure out a parabola that matches that just by itself. Because 2 points determine a line. How many points determine a parabola? 2? 3. Watch this. Do you agree that I could make a parabola that looks like this? Okay? Or like this. And I can still go through those 2 points. Okay? So in order to figure this out, we're going to abandon this, and we're only going to use half of it. The half that we're going to use is the fact that this takes 4 seconds. I'm focusing on the right side of this. And this means we're going to use this free fall equation instead of the other 2. Yeah. No, because it's the 4 seconds right here. Okay? Yeah.
Could you use the first 4 seconds if you wanted to? Why do you have to use?
Well,
Because it's going down.
yeah, just because it's going down. But you could use the other one
Okay.
for that. This more closely simulates the fact that if I drop a ball, let's pretend I was at the water tower, at the wind turbine, and I dropped the ball. This is what would happen as the flight path. Okay? So watch this. We're going to use this function. S of t is equal to 1/2 gt squared plus h sub 0, and we're going to plug in the numbers that we know, and we're going to find out h sub 0. Okay? All right. S of t is the height of the ball. What I'm going to do here is I'm going to say, I want to know when the ball hits the ground. So my position here, my height, this is 0 feet. 0 feet. And we'll plug in everything else. 1/2. What did we say yesterday for gravity? -32. Okay? T squared. Look at this. I know that it took 4 seconds for it to hit the ground. So I'm setting the position function equal to 0, and I'm going to solve for h sub 0. Now, fill in some things here. This is feet per second squared. This is seconds. You can see we're going to have seconds squared. They'll cancel with the second squared here, and we're going to be left with feet. Okay, what do we get from this? Half of that, that's -16 feet per second squared. This is 16 seconds squared plus h sub 0. Okay, 16 times 16, that's 256. This is negative, so it's 0 is equal to -256 feet plus h sub 0, which means that the initial height of this thing had to be 256 feet high. Okay. This is how we create the form. This is the formula that's going to get us there. So that means for this particular thing, S of t is equal to, we'll put all the real numbers in here, -16t squared plus h sub 0 plus the 256. What the heck does this mean? Yeah.
When you plug in the time, you can find out where.
Exactly. So let's plug in some numbers. Now, we're simulating. Remember, we abandoned the original one, and we're going to be able to develop this one from this one. But this one, we're going to say, let's pretend we're at the top. We're at the top of where the ball was dropped, and we're letting it drop. So if I say, what's S of 0? That's saying, how high is the ball at the moment that I release it? And the answer is, it's 256. It's right here, 256. And then I say, okay, what's S of 1? One second goes by. How high is the ball? 240. That means 1, 2, 3, 4. It's at 240 right here. This is a position function. S of 2. What do you get? 180 something? Come on, come on, come on. There's 8. 192? 192. At 2 seconds, this thing is 192 feet high. You see what I'm doing with this? And finally, what's S of 4? S of 4 is 0. S is our position function. It tells you how high the ball is above the ground at any given time. It's position. And that's how we get to this one. Okay? But now, this one is not exactly what I want. What I want is that one that looks like the one on the board. So I have to somehow shift that parabola. How can I shift this parabola, which does exist over here mathematically? How do I shift it so that the 4 is in the middle? Don't reflect it. How do I turn this? Subtract 4. Exactly. So see this equation right here? Watch. If I write a new equation, S of t is equal to negative 16 times t minus 4 squared plus 256 what I've just done now is I've taken this, and instead of writing just t here, I shifted it to the left, to the right 4 units. This graph, would you agree that this graph looks like this? Starts at 0. It's got our parabola here and here. If we knew this was true, did we just shift that graph to the right 4 units? It's transformational parabolas. Okay? That's that function. But I don't know, mine looks different than that one. Mine looks like negative 16x squared plus 128x. But I got this. Okay, if we expand this out, that's what we're going to do right now. We're going to expand this, do a little algebra. We should come up with that one right there. So here we go. S of t is equal to, we got to save the negative 16 for after expanding this. This is t squared minus 8t plus 16 plus 256. Then I'm going to distribute negative 16t squared plus 8 times 16, that's 128. T, 16 times 16 is 256. Huh, look at that, they add up to 0 right there. I wonder if that happens all the time. And so these add up to 0. So therefore, S of t is equal to negative 16t squared plus 128t. And what we just did here was, only knowing the fact that the ball was in the air for 8 seconds, we just wrote the position function for the entire time that it's in flight. That's the graph of that function. That make sense? Now, this is actually, there's no calculus here. Sorry, we're not there yet. But here's where the calculus comes in. I can ask the question, hey, how fast was that ball moving? What was the instantaneous velocity of the ball at time equals 2? Well, on this graph, if I go over here, time equals 2, it's right here. How fast was the ball moving at exactly time equals 2? This slope is the velocity of the ball. Amazing. It's really cool. So how do we find that out? How do we find the slope of the line tangent to the graph of the position function at time equals 2? Bless you. I need ideas. How is it possible to find the slope of a line when you're only given 1 point? I want to know what the slope of the line tangent is right here with only using 1 point. How is that possible? Have we ever come across a place, a formula or an idea that allows us to find the slope of a line tangent to a curve, a function, at any given point? Harry? The derivative. That's what we did yesterday. Okay? So watch this. The formula says this. The derivative of f of x. Actually, I'll say derivative of f of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That's a mouthful. We're supposed to somehow use this monster, and the answer is going to be able to, the answer to that thing is going to tell us how fast this ball is moving at any given second. Okay, so let's do it. So the derivative is the limit as delta x approaches 0 of, now this was f. I have a function called s. Okay, s. And so what I'm going to do is I'm going to find s, watch what I'm going to do here, s of x plus delta x minus s of x all over delta x. Because I'm not using an f function, I'm using an s function. I hope this works. Okay, here we go. This is then the limit as delta x approaches 0 of, okay, what's s of delta of x plus delta x? What is s of x plus delta x? Say it again. 8? S of 8? Nope, we don't have any numbers here. Look at this. S of x plus delta x. Sure. Remember the smiley face? Plug in the smiley face, f of smiley face. So what we got here is we're going to take x plus delta x, and we're going to plug it in for t, wherever the t is. So this is negative 16 times x plus delta x squared plus 128 x plus delta x. Step away and look at this. You see this is where the t's are? That's all I did. Wherever there was a t, that's where I put this bugger. Because we were told, what is s of x plus delta x? I don't know. Just take that and plug it in for every t. So we get this. So this section right here is this whole thing right here. Minus s of x. S of x. Well, s of x, that's the whole, we're going to plug an x in there. So I got to put parentheses in here. That's negative 16x squared plus 128x. And this whole thing is over delta x. Now we just have to figure out the answer to this.
So
What?
it looks weird that it's like really drawn out on the top and then it's just like delta.
Do. Yeah. Okay. Now put on your algebra hats here. Let's go. The limit as delta x approaches 0 of... I'm going to expand this. Okay, now stick with me. Negative 16 times, I'm going to expand this. This is x squared. It's all it is, a binomial squared. X squared plus 2 times x times delta x plus delta x squared. And this delta x, these two are glued together. You get the same thing if you did FOIL, but I hate FOIL, so we don't do it. Then we're going to distribute. Plus 128x plus 128 delta x plus 16x squared minus 128x. All over delta x. Whew. No wonder Descartes died. Okay, let's keep going. We're going to distribute this now. We're going to look for things that cancel. So the limit as delta x is approaching 0 of negative 16 squared minus 32x delta x plus, minus 16 delta x squared. Remember, those are glued together. Plus 128x plus 128 delta x plus 16x squared minus 128x. All over delta x. Whew. Do we end at 121 or 3?
3.
Yes. This is way too short, isn't it? Way too short. Okay, does anything cancel? I spy 16x squared and negative 16x squared. 128x and the negative 128x. Okay. Do you see a delta x in all the rest of them? That's what I see. So we're going to write this as the limit as delta x approaches 0 of, I'm going to pull out a delta x out of the top. So what do I got here? Negative 32x minus 16 delta x plus 128 all over delta x.
Can you just think of
Boom, 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 boom. Is delta x actually 0? No. So we can divide those out. That's no problem. And then now we say the limit as delta x approaches 0 of negative 32x plus, or minus 16 delta x plus 128. Does anybody remember how to answer that from last year? You can now allow delta x to approach 0. So the final retail answer to this thing is negative 32x plus 128. Write that down, and we're going to figure out what the heck that means tomorrow. That was fun. We do that all day.